So this is our sushi server robot. We are group 69. I'm Diego Montoya.
And my name is Victor Menento. So, as the overview of the project, we wanted to design a robot that would deliver food from the kitchen to the table in a restaurant setting and from the table to the kitchen. All right, so our initial inspiration for this idea was the conveyor belt system that they would have at sushi restaurants to deliver dishes from the kitchen to the table and back.
So this is our equipment list. We used six different types of resistors. Uh, Four of them was for our uh, table system, and the last one was for our sound circuit. We used four push buttons, 10 microfarad capacitor, a speaker with an amp, which was just a little portable Bluetooth speaker that had a auxiliary input or an auxiliary input to it. A micro SD card reader. We used the Smart Robot Kit. That was the basis of our whole project. We switched out the Arduino Uno for an Arduino Mega, and we used a ton of wires.
All right, and we also 3D printed a ton of parts. So there were a lot of parts of the robot that needed to be moved around, and the only way to really mount them to the robot would be to 3D print some mounts for that. So we printed a ultrasonic sensor mount, so we can mount that without using the servo. We also printed a line sensor bracket, so we can move the line sensor to the middle of the robot. And then we also printed some breadboard clips so that we could easily attach the breadboard to the robot without it being unsecured. And we had to create several various sized spacers to be able to have everything work.
So as my partner just explained, we created a bunch of 3D parts, and so I'm here to show you that. So as we see in the top left picture, that is the clip for our breadboard. We put it in the position where normally a servo and ultrasonic sensor would go. We put it in that area. But as you can see on the top right picture, the modification to the ultrasonic sensor is we got rid of the servo because we don't need that as it is just following a line. And we're just using the ultrasonic sensor to find objects that are directly in front of it. We just got rid of the sensor to save space, mounted the ultrasonic at the bottom, try to move everything to the front to conserve space that we could use elsewhere. In the bottom left picture, we can see the platform that we use to deliver our sushi. And in the bottom right picture, we can see where we put the ultrasonic sensor. This was mainly so that we could do really sharp 90-degree turns whilst not losing the line. Uh, we 3D printed special mounts for it to go there, which is what my partner explained in the previous slide. So in the schematic, the circuit diagram, I didn't show the original robot because I thought it would be monotonous to show that because everybody has that. So I'm just showing you the modifications that we added. So obviously the Arduino Uno is replaced with an Arduino Mega so that we can use the ports that are on the right side, the 22 through 53 ports, I believe is what it is. Yeah. Uh, on the left side of the breadboard, you can see what we use to control our robot by sending it to which table. That this is the circuit on the left tells the robot where to go. The circuit on the right is what we use to control our speaker. Next slide, we just have a nice picture of what it looks like on the robot. It's the same thing as the schematic. Next, we move on to the track. As you can see, the track is made out of paper. For the purposes of testing, it's real distinct difference between the line and the paper. It makes it easier on the line tracker for it to know where to go. The robot typically starts off in the kitchen and it'll be facing towards you, and it'll continue to table 1, table 2, or table 3. Whenever the robot is told to go to the kitchen, it'll be placed like how it is seen in the picture, and it'll continue on to the kitchen.
All right, so our code is a giant behemoth of complexity. We had about 300 lines in our final code revision, and this image just shows a flowchart of the main functions. So from the start of the function of the program, it wants to determine the destination based on the button press. So it'll be listening for which button is being pressed on the robot on the breadboard, and it will know from that which place or which location the user wants the robot to go to. And then it goes on to the navigate function. It is responsible for all of the functions that get the robot from point A to point B. So it does some math and it calculates the offset, which determines how many markers, as seen on the track right here. So the perpendicular lines are markers. It determines how many markers the robot needs to pass to get to its destination. And then it does a line track, and it can turn around 90 degrees, and it does the line track to the destination. And then once it arrives at the destination, it plays the appropriate audio file that we have saved on the SD card. And once it's arrived there, it ends the program, and then it resets back to the start. And then for the line tracking itself, we do have a special kind of flow chart for that. So it starts whenever the line track function is called, it goes straight to sensing the line. And if all the sensors are detecting the line, meaning that it's hit a marker, then that means that it is getting closer to the destination. And we use that as like a frame of reference to know how far it has gotten along the track. So if it counts the number of markers it needs to count up to, it ends the line track, and that's how we know it is at point B. Otherwise, it would do a distance test to see what's in front of it. And if there is something less than 10 centimeters away from it, then it will stop and then play the appropriate sound. And if there is nothing in front of it, then it will line track just like normal, as was worked on in the lab. All right, so we did have a couple problems with the robot. The first one was the traction, or the friction between the tires and the track. We did have a lot of issues with that, specifically with the turns. Every time the robot would try to turn, some of the times the tires would lift up from the track or not have enough traction, so they would just be free spinning, and the turns were, as a result, very, very irregular. Also, it says the wheels turning at different speeds, and that was because of the power delivery to the wheels. We did lower the power to all of the motors, and that created an issue with the torque at the wheels, and that caused the wheels to turn at different speeds sometimes. Weight distribution was an issue at the beginning of the project, but it did not become a big issue towards the end of it. There was also a lot of instability in the motor shafts and the motor mounts, which caused the robot, if going in a straight line, to veer off to the left or the right. So the line sensor detection was an issue because of the traction and the inconsistent turning. And also, we weren't able to program it in completely, but it would have been nice to have the ability for the robots to determine exactly which direction it's facing, maybe with the magnetometer, and its exact location on the track, so that we know concretely if it's going to the right destination and if it's facing the right direction. So as the conclusion, we were able to achieve our goal of building a robot that could deliver food to and from a table. It worked actually quite beautifully at the end. Despite all the issues, we were able to get some really nice videos of some clean runs and demonstrates all the functions working.